G that's defined over R. And always the most important example is no defining equations. G is GLNC, and G of R is GLNR. This group, as I said, we're always taking to be connected, but this group of real points might be disconnected as GLNR is. Okay, and well, that's where we're always going to be working. So what we're going to find is that this set of all representations of G of R is basically a complex algebraic variety.
Can I ask a question?
Yes, absolutely.
So this is precise if V is finite dimensional and V can make sense if it's infinite dimensional?
It's imprecise even if V is finite dimensional because the groups we're interested in are not finitely generated. So even this is only approximately a reason. Yeah, we're going to find we're going to define irreducible representations and see how to parameterize them, and we'll see that we're getting a complex algebraic variety. I don't really know a priori how to prove that before you're done with the classification. Okay, but as I say, these are nice and easy to describe, but what we want to understand are unitary representations. So first, we're going to look at representations that have an invariant Hermitian form. So remember, what unitary means is that the representations live on a Hilbert space. So I'll write so roughly the picture is a representation lives on a complex vector space. A unitary representation, unitary representations live on H pi, which is a complex vector space with an invariant form which is positive. So the So in between these two places, we can look at Hermitian representations. These things live on a vector space V pi, and with an invariant form like this, but not assumed to be positive. So that's the picture. Sorry. Yeah. I mean, we're. So because the representation is irreducible, non-degenerate is the same as non-zero. So we have these containments, and what we're going to see is that this first thing looks like an algebraic variety over the complex numbers. This thing is going to look like the real points of such an algebraic variety. So this well, I would call this beautiful and this okay. And then, and well, I don't mean to cast aspersions. This was found. This description was found by Langlands. This description by Knapp and Zuckerman. And this description down here, this is the atlas thing, and this is going to be something defined by inequalities. I mean, I don't know very much or anything about real algebraic geometry, but it's a standard thing to worry about real algebraic things cut out by inequalities. And that's what's going on here. Well, if in this metaphor, this is really ugly. We're going to try to tell you beautiful things about this, but it's just difficult. Okay, so that's the picture, and so we want to understand these containments, and what we want to do is, well, in particular, what I want to do in these lectures is tell you about this Langlands classification of
Sorry, this is an ugly question, but
yeah.
So you say ugly, but isn't that answer kind of in the nature of the question? Or
So yes, yeah. So that's partly what I mean is that the questions are getting uglier. The question of defining an algebraic variety, you know, the theory of quadratic surfaces over C is beautiful and simple.
But it's not a judgment on the type of answer you get.
That's right. That's right. Yeah, when you start taking real points of quadratics, then there are a bunch of cases, and then when you get these hyperboloids of two sheets and you want to decide which sheet you're talking about or something, it takes a while.
I would call it complicated.
Yeah, it's complicated, yeah. Okay, so I'll tell you about the pretty part. I'll tell you about this Knapp-Zuckerman identification, how to put a sort of real structure on this algebraic variety so that the Hermitian things are the real points. And what we're going to do, once you have this invariant Hermitian form, the big idea is what we want to do. Oh, I'm not supposed to use. What we want to do is calculate a signature. For this form. It's got sort of a positive part and a negative part, and we want to calculate the positive and negative parts. And once we know how to calculate the positive and negative parts, we do that, and if there aren't any negative parts, we win. That's the story. So that's what I'm supposed to do. So I think the next thing, this is just a summary of what I've said so far. What I want to describe this week is the nature of this atlas classification of the unitary representations, the equivalence classes of irreducible unitary representations of a real reductive group. And then I'm going to do this first by telling you that I've got to put the white hat in with a different relationship to braces, but anyway. The Langland's classification of all the irreducible representations. Then I'll tell you about the Knapp-Zuckerman classification of the Hermitian representations. And third, I'll tell you about how Atlas computes the signatures of these invariant Hermitian forms. And the last thing is to look at the answers to these signature computations and see when the signatures come out to be definite. That's the story. So what I'm going to do in the last 10 or 15 minutes is talk about what the Langland's classification looks like. And what I want to do is I want to assume that you may know about highest weight representations, the material which is in Humphrey's book on Lie algebras, or in many other places. The classification of highest weight modules for a reductive Lie algebra is very simple. And I want to talk about that theory and say the Langland's theory is just like that. So how does highest weight theory go? So in highest weight theory, you start with a complex reductive Lie algebra and a Borel subalgebra, which is a Cartan and a nilpotent part. Bernstein, Gelfand, and Gelfand introduced a category of G modules, And the conditions on the G modules that they imposed were these three. First, the G module is finitely generated. Means inside the module there's a finite dimensional subspace, so that if you apply the universal enveloping algebra to that subspace, you get V. Second requirement is that the action of the Borel subalgebra is locally finite. Means that if you take anything in V and apply the enveloping algebra of the Borel subalgebra, you get a finite dimensional space. The third requirement is that the action of the Cartan subalgebra H is semi-simple. So if I have a linear functional on H, I want to write V gamma. I'll put V gamma up here. Call this the gamma weight space. Okay, so the assumption is that V should be the direct sum of all these weight spaces. And we want to understand, we want information about representations in this category. Well, what kind of information might you ask for? If you have a representation in this category, one thing which is true is that, well, the dimension of the weight spaces, the dimension of the weight space, that's some sort of function of gamma. And what kind of function of gamma is it? Well, it's what's called almost polynomial. I'm not going to write the definition, but you can say kind of precisely how this dimension varies with gamma. Another important fact is that V has a formal character. And I'm not going to recall what the Weyl denominator is, but or what formal character means, but that's what it looks like. You have a finite sum of exponentials in the denominator, the numerator, and then the denominator is something fixed. Okay, so we want to know how you make representations in this category. And
the quotient is not finite? Would you say it's finite?
So this numerator is a finite sum.
Yeah, the quotient is infinite.
The quotient is infinite because the denominator is also a finite sum, and so when you divide, it's infinite.
Oh, what is it?
Well, I mean, it might be infinite, yeah. Yeah, the Weyl character formula is, you've got a finite quotient. Okay, so how do you make representations in this category? Well, the basic construction is this construction of what are called Verma modules. One of my favorite facts about representation theory, this notion of these modules, you can look in the literature and find out what the history of the notion is, and it's very clear. They were invented by Harishchandra, but there are too many things to name for Harishchandra, so these are named for the person who made a further study of them 10 years after. So that's something to encourage all of us. So the description that you can read about in Humphrey's book for highest weight modules is based on these Verma modules. So the first fact is that this Verma module has a highest weight vector. It it has the weight lambda in it, and that weight is fixed by this nilpotent subalgebra n. The second fact is that this Verma module has a unique irreducible quotient module, which I'll call J of lambda. This notation I of lambda and J of lambda is not at all standard for highest weight modules. I'm using it because it's parallel to the notation that is standard for group representations. So it would be much more common to call the Verma module perhaps M of lambda and its irreducible quotient L of lambda, something like that. But this I and J is the group representation standard.
But note that irreducible is J, not I.
Yes. Yes. So the I stands for induced, and the J stands for quotient of I. I don't know. Then the classification theorem says that any irreducible in this BGG category is one of these irreducible highest weight modules. Well, it's the unique irreducible quotient of some Verma module for a unique weight. So, in particular, this says that the irreducibles are parametrized by this complex vector space, H. So, this is the irreducible modules look like a complex algebraic variety. So, I'll write that over here. These things are parameterized by H star, which is a complex vector space, and therefore is a complex algebraic variety. So that's wonderful.
But inside is somehow a discrete set of finite dimensional.
That's correct. The property of being finite dimensional is, well, it's defined by inequality. It's defined by infinitely many. Well, I don't know a good way to say the definition. Inside this set of all highest weight modules is a discrete set of finite dimensional highest weight modules. And I was trying to think what kind of condition on lambda is being finite dimensional. And it's kind of funny. I mean, they're not, yeah, I haven't thought carefully about this. But yes, I mean, this certainly contains, all right, lambda plus the dominant integral weights. So this is some sort of cone in a lattice. In the semi-simple case, it's a lattice, but anyway. And these are the finite dimensional representations. Yeah, so that is a bit parallel to this unitary problem. The class of representations in which you might actually be interested is, it sits inside here, but in a somewhat complicated way. So this is what we're going to try to do for group representations. And what's the next slide? Well, so I want to say, remind you a little bit about how this is done for highest weight modules. So we have this Borel subalgebra. I'm going to write capital delta for the system of roots and delta plus for the positive roots defined by m. And that introduces a partial order on weights. You say that mu prime is less than or equal to mu if the difference mu minus mu prime is a non-negative integer combination of positive roots. So that's the ordering. And then if you have any module, if it's not 0, then you can find a maximal weight subject to the requirement that this mu weight space is non-zero. And if you have such a maximal weight, then the weight space is killed by the action of n. And, well, if you put 1 and 2 together, it tells you if you have a non-zero module, there's a weight where the weight space is contained in the n fixed vectors. And this fourth statement is unrelated to the first three. It says if you take any Verma module, that the G homomorphisms from this Verma module to V are given by the H homomorphisms from this one-dimensional lambda into the n invariance of V. So this 1 to 3 is what says that there are highest weights, and the proofs of 1 to 3 are formal facts about lattices in vector spaces and what the action of n does to a weight space. This should have been subscripts here. I was writing weight spaces with subscripts, so this should be V subscript mu prime and subscript mu prime plus alpha. So that's how you prove 1 to 3. And then 4, the definition of I lambda is this. And this construction of a module, this kind of construction is called a change of rings functor. And I've gone from a module, the C lambda for the small ring U of B, to a module for this big ring U of G. And in that setting, there's a formal identification that this maps over the big ring are the same as maps over the small ring. And you just calculate those and you get this. Yeah, so this isomorphism here is a change of rings theorem, and the second one is the fact that n acts by 0 on C lambda. So this proposition is what lets you do the classification of highest weight modules. I think maybe, well, okay, I'll just say this, that in category O, there are 3 big ideas that matter. The big one is that these Verma modules are defined by a change of rings functor, and therefore that you get this universality property of the Verma module. And the third thing is that highest weights exist. That if you have, in fact, any non-zero module in category O, that it has a non-zero space of n invariance. So this 1 and 2, these are things from the Cartan-Eilenberg book on homological algebra. This number 3, this had to do with the manipulation of weights in H star. And what comes out is that the irreducibles correspond to H star, and the characteristic property of this bijection is that the weight lambda appears in the n invariance. So what I'm going to do tomorrow is apply these same ideas to GK modules. The change of rings functor that comes up is not projective. This U of G is a projective U of B module. So this tensor is an exact functor. In the GK module setting, the corresponding change of rings is not projective, and so in addition to tensor, you need to use derived functors of tensor, these pores. And in the same way, these n invariants, which you can think of as zero cohomology, have to be replaced by the derived functors higher cohomology. But what will come out is that the irreducible representations are parametrized by essentially characters of Cartan subgroups of G. And the characteristic property will be that the weight for the Cartan appears as a cohomology class of the representation. So that's what I will start talking about tomorrow. Thanks.
Any questions or comments? If not, then we will reconvene at 10:45. Is that right? According to the schedule? What is it?
10:30.
10:30. Okay, very good.